I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just pray that you'd be with us today. Help us to glorify what you do, glorify you and what we do, rather. And I just pray that you'd give us insight into Laplace transforms and how they work, Lord. In your name I pray. Amen. All right, so there's two ways I can go here. The one way would be to try to give you a motivating example at the start, just to show you what the Laplace transform does for us. The other way is to build up properties of the Laplace transform carefully for about a half hour and then give that example. I think this year I will give the big picture example at the start. Now, so necessarily then, this example I'm giving you will involve calculations that we have not yet learned how to do. All right, but I think it might be helpful actually to solve a problem like this. Here's the problem. If I have, say, y prime prime plus y equals to u of t minus 1. Now, this u of t minus 1 is an interesting function. It's equal to 0 if t is less than 1, and it's equal to 1 if t is greater than 1. Actually, I don't care what it is at 1. But this is the unit step function, right? Like a switch. And let's assume, to keep things relatively simple, that y of 0 is equal to 1, and y prime of 0 is equal to 0. So let's solve this thing. Now, in our current way of thinking, this would have been a pain. Because what I'd have to do is I'd have to solve it from time 0. Right? Find one solution, and then I'd have to find a different solution for time beyond 1, and then I'd have to fit those solutions together using continuity or something, right? But the Laplace transform gives us a technique to solve such problems in one fluid motion, all right? So what you do is you take the Laplace transform, all right? And it works, it turns out that the Laplace transform of this differential equation, we call it star. So the way it works is we get s squared times big Y, all right? And then minus s plus big Y is equal to the Laplace transform of u of t minus 1 of s. Now, it turns out the reason that there's a minus s here is because the y of 0 is 1. So the reason that s appears is because of the initial conditions. Now, the Laplace transform of the unit step function, I might not even get to talking about today, but we will talk about it soon. And that works out to, if I remember right, 1 over s e to the minus s here. So by taking the Laplace transform of star, I've turned a differential equation into an algebraic equation. So what I have then is I've got s squared plus 1 times big Y is equal to s plus 1 over s times e to the minus s. So I can solve for big Y by just dividing. You might notice it's the characteristic equation in S, right? Characteristic polynomial, rather. So I get s over s squared plus 1 plus 1 over s times s squared plus 1 times e to the minus s. At this point, I have solved for y algebraically, all right? So the next stage in the game is to say, okay, well, this 1 over s times s squared plus 1, I can use partial fractions to rip that apart into pieces. That's something like a over s plus bs plus c over s squared plus 1. Multiplying both sides by the denominator gives me 1 is a times s squared plus 1 plus s times bs plus c, which gives me 1 is equal to s squared times a plus b plus s times c plus a. And now I can equate coefficients of the constant term, the s term, and the s squared term. Equate coefficients. From 1, we get 1 is equal to a. Well, that's a nice equation to solve, right? It's kind of, okay, there we go. S, what do we get from s? From s, I get 0 on the left-hand side, and from the right-hand side, I get c. I also like this equation. I think odds we can solve the first two equations pretty high. Third equation, s squared coefficients, what do we got? We've got 0 is equal to a plus b. Aha! So, lo and behold, we have a equals 1, b equals minus 1, and c is 0. So that completes the partial fractions part of the calculation. And so I'm going to go back over here and use that. What I have then here is s over s squared plus 1. That's already basically in its finished form. And then plus, in view of my partial fractions work over there, 1 over s minus s over s squared plus 1, e to the minus s. All right. Turns out making it in that form allows me, through the theory that we'll discuss and work out today in the next class probably. Well, now it's in a form that I can take what's called the inverse Laplace transform. So taking the inverse Laplace transform of this, inverse Laplace transform, the inverse Laplace transform of s over s squared plus, first of all, the inverse Laplace transform of big Y is little y. Little y is what we're looking for. It's the solution in time t. The inverse Laplace transform of s over s squared plus 1, well, that's cosine t. All right. Now, this business over here is a little bit trickier. If this thing is g of s, all right, then the inverse Laplace transform of that is little g of t. And little g of t actually here is, you can see it's actually 1 minus cosine t. I'm not saying you can see it at the moment. Think of your future self. If you can imagine time traveling back 2 weeks, well, a week from now, give or take. This should make perfect sense to you. 10 days from now. Before the end of the semester. Definitely before reading day. Okay. Some point in the future. Not too long from now. How do we say in Mystery Science 3000? Next Sunday, 80 or something. That's right. So plus. So what I do is 1 minus the cosine of t minus 1 u of t minus 1. This is by a theorem. And there you go. That's the solution. We solve t less than 1 and t greater than 1 all at once. And the solution comes prepackaged with a unit step function, which accounts for the abrupt change in the forcing function at time 1. So the method of Laplace transforms is quite beautiful in the sense that it naturally deals with discontinuous forcing functions. That's a lot of the reason we're studying it, is we don't have to break up into cases. Do you notice anything else about this calculation? Admittedly, you probably don't understand. I mean, I don't think you understand the parts of it yet. Although some of you have seen some Laplace transforms in that circuits course somewhere, right? No? I see some nodding, but you notice that that's the solution to an initial value problem. Did I have to fit constants to the end? I did not. They're built in. They are rolled into the Laplace transform itself. To take the Laplace transform, I actually need to know initial conditions. So it folds initial conditions into the solutions from the outset. And it deals with discontinuities. These are the two main features that I think are really, really exciting and interesting about Laplace transforms. All right, so This is what it does. Now let me show you actually what it is. Definition. The Laplace transform of f of t is a new function. It's a function of s. And it's defined by the improper integral from 0 to infinity, of e to the minus st f of t dt. Now, if you're a thinking person, what's your thought at this point? There's really only one thought I think that a reasonable thinking person can have at this point, which is, why on earth are you doing that? I mean, that is a bizarre thing to do. Integrate across an exponential function from 0 to infinity, the function that you're given, to create a new function of a new variable s. This is weird, right? If you'd like a motivation for this, you can find one in MIT's open courseware. Professor, I think, Mattock, he spends the better part of 30, 40 minutes motivating this as it relates to some discrete transform. So if you want motivation, it can be found. But I'm not entirely sure you guys know about that discrete transform he's talking about either, so I'm not sure that's actually helpful motivation for you. Anyway, the motivation I'm trying to give you here is that it does this. That should be motivation enough, although admittedly this is weird. So, weirdness aside, what are the fundamental properties of the Laplace transform? So first of all, you can see that if we had C1F1, right, plus C2F2, it would be what? It would be C1, the Laplace transform of F1, plus C2, the Laplace transform of F2, assuming that these Laplace transforms actually exist. In other words, the Laplace transform is linear. It's a linear transformation. It's a linear operator, if you like. But it's a kind of different operator than we're used to. I mean, here's notation that we like to use. The Laplace transform of little f of t, all right, of s, is equal to big f of s. This is not an antiderivative. In this world that we're living, that's the notation for the transformed function. Electrical engineers like to say s is the frequency domain, whereas, of course, t is the time domain. So the Laplace transform takes us from the time domain to the frequency domain. I will let the electrical engineers explain to you why that terminology is reasonable. So here's two pretty standard notational schemes. We can either use the L to explicitly denote the Laplace transform, or we can change lowercase to capital to indicate the transformation. All right? Which do you want to use? Well, it depends on what you're doing, right? Like over here, I use both notations. I use the script DL notation here to communicate that I was taking the Laplace transform of this thing, right? But I use the big Y notation over here because it allowed me to do the algebra more elegantly, right? Anyway, what else can we say? Well, them's the basics right there. It's linear. It's that. I will just say this remark, and I won't get into it much at the moment. Maybe if I feel guilty next time, I'll get into it. If f of t, if you can write the value of f of t is less than or equal to m times e to the alpha t, all right, for some alpha, let's say for t greater than 0 and for some alpha in the reals. If you can do this, then your function is said to be, then f is said to have so-called exponential order alpha. All right? And if you study that, you can prove that if a function has exponential order alpha, then its Laplace transform exists. All right? And maybe I should put a minus. I can't remember the precise definition. Maybe if I put if I assume alpha is positive, I probably need to put a minus there. Right? Would that make sense to you? Let me just, I'm not sure this is, hey, you know, it's my class. So here, minus and alpha is positive. I don't think that's at odds with the usual definition. See, what that condition is saying is that if you can fit the function under an exponential, right? So if you think about the graph of that function, here's this exponential. And this condition is saying that the graph of the function is under that exponential. What can you say about the integral of an exponential of that kind of argument from 0 to infinity? One of the things we learn in calculus 2 is that the integral of the exponential of minus a negative real multiple of t from 0 to infinity converges. All right? So that kind of exponential, m e to the minus alpha t integrated from 0 to infinity converges. So of course something smaller than it will also converge, right? And if the absolute value of the function's integral converges, then the function's integral converges. So, all right, but that's pretty much all I've got to say on the analysis side of things in here. Pretty much we're just going to go and calculate things, and hopefully they converge. So, what's the first thing you would try to calculate then? Example 1. How about the Laplace transform of the number 1, or the constant function 1? What would that work out to? We got integral from 0 to infinity of what? E to the minus st times 1 dt. All right. So that is, by definition, the limit as, let's say, b goes to infinity of the integral from 0 to b e to the minus st dt. For those of you who are rusty on your Calc 2. So that's the limit as b goes to infinity of what? Integral of that with respect to t is minus 1 over s e to the minus st, right? I got to evaluate that from 0 to b. So what's that give me? That gives me minus 1 over s e to the minus sb, right, from the upper bound. How about the lower bound? What's that give me? What's e to the 0? 1, so we get plus 1 over s, right? So if s is positive, what can we say about that first term? What's its limit? It's 0. Very good. Congratulations, you just calculated your first Laplace transform from the definition. So therefore, the Laplace transform of 1 is in fact equal to 1 over s. It probably wouldn't hurt us at this point to say, you know what that means? By the way, the inverse Laplace transform of 1 over s is equal to what? Is 1, right? If the Laplace transform of 1 is 1 over s, the inverse Laplace transform of 1 over s is 1. So it's a 2 for 1. It's like for every derivative, you get an antiderivative. For every Laplace transform, you get an inverse Laplace transform. And we need both to solve differential equations. Any questions? All right, good. We got this covered. Let's see. Up next, example 2. Let us calculate the Laplace transform of an exponential. Right? So let's calculate the Laplace transform of e to the at. All right? Laplace transform of e to the at. Okay, so by definition, that's the integral from 0 to infinity of e to the minus st times e to the at dt, right? Which is actually the integral from 0 to infinity of e to the minus parentheses s minus a t dt. Would you guys be terribly offended if I omitted the limit notation? No? It's okay? Okay, all right. It'll break your heart. Now this.
Will you be offended if we omitted in a test?
Not as long as it's not an omission which leads to an error. I mean, you got to remember L'Hopital's rule and stuff like that, right? I mean, like indeterminate limits, they'll still learn determinant even if you don't write the limit. So be careful. But yeah, sure. Don't tell the other professors. Let's hear. Minus 1 over, this is minus 1 over s minus a, e to the minus s minus at, and you got to evaluate that thing from 0 to infinity. Of course, this is a notation which implicits a limit. All right. But anyway, there's nothing terribly complicated or controversial about this. And in terms of the limiting process, it's actually pretty obvious what goes on here. This is e to the s minus a times infinity. Do not tell my Calculus 2 students I did this. Thank you. Plus 1 over s minus a. Now there's fine print, right? There was fine print over here in the previous example too. I said it, but I didn't write it down. This what? That limit is only 0 for s positive, right? So over here, s minus a is a positive thing, right? S minus a is positive, and this argument to the exponential is negative only when what? We need that s minus a is positive, right? In other words, we need that s is greater than a, right? But given that condition, we have the following. The Laplace transform of the exponential, e to the at, of s is equal to 1 over s minus a. For s greater than a, all right? Fine print. Now, admittedly, I'm a little bit embarrassed that I've done this example for you because usually I just let the next theorem cover this for us. The next theorem says the following. Theorem, the Laplace transform of e to the at times f of t of s is actually equal to the Laplace transform of f of t at something. All right? We'll complete the theorem as we prove it. How about that? Proof. So calculate the Laplace transform of e to the at f of t. What's that give you? We got e to the minus st, e to the at, f of t, dt by the definition of Laplace transform. And then we can combine those exponentials just like I did in my example 2. That's e to the minus s minus a times t, f of t dt. So you just got to walk back a couple feet, tilt your head, squint, and you should see that that's nothing more than the Laplace transform of f of t at what? What have I done? I've replaced s with what? What's that? No. S minus a, right? So this s goes to this s. in the same way that this s minus a goes to this s minus a, which is, by the way, exactly what we saw over here, right? Because if you think about this is also equal to the Laplace transform of e to the at times the 1 function, right? So you can see this so-called shift theorem in action if we study examples 1 and 2. This is called the shift theorem. All right. So that's kind of neat. You're like, you haven't talked about, it's been like at least an hour of lecture before, since you've talked about complex variables, and I really would like you to get back to complex variables because I like it a lot when you talk about complex variables. So I hear what you're saying, and I will bow to the pressure to talk about complex variables at this point. So thank you for that. This is my example 3. Sorry. All I'm actually going to tell you is that example 2 still makes sense if a is a complex number. So if lambda is, say, alpha plus I beta, then the Laplace transform of e to the lambda t is in fact equal to 1 over s minus lambda. You can study this carefully. The usual rules of complex variables still make sense here in the sense that we're doing integration of the real part, integration of the imaginary part separately. There's still real integrations. It's not an honest to goodness. I mean, let me expand on this. This means the Laplace transform of e to the alpha t cosine beta t plus I e to the alpha t sine beta t, right, of s is equal to 1 over s minus alpha minus I beta. That's great, but we would like for that I to be in the numerator, not in the denominator. So we need to rationalize that complex fraction. But we know how to do that, right? We know what we need to do. So what we do is we take this and we multiply by s minus alpha, parentheses, plus I beta, over s minus alpha, parentheses, plus I beta. Right? Notice that over here, you can look at this as the real part is s minus alpha, and then you've got minus I beta, right? So I'm multiplying by the complex conjugate over the complex conjugate of that to rationalize that fraction. On the left-hand side of things, I can pull the I out, see, because that linearity I just erased, it also holds for complex constants in the natural way. So the Laplace transform of e to the alpha t cosine beta t of s plus I times the Laplace transform of e to the alpha t sine beta t of s is equal to, multiply this stuff out. What you got? You got yourself an s minus alpha plus I beta, and downstairs you got s minus alpha squared plus beta squared. Now, all we got to do is equate real and imaginary parts of this equation. What does the real part tell us? Yeah, the Laplace transform of e to the alpha t cosine beta t of s is equal to what? We got an s minus alpha over s minus alpha squared plus beta squared. And the imaginary part, what's the imaginary part tell us? you've got to strip off. We're just looking for the coefficient of the I. Not the I itself is not included. So look at it. There's this piece has to match that. So we got excuse me, beta over s minus alpha squared plus beta squared. There you go. There's the Laplace transform of sine or cosine times an exponential. If we use the shift theorem, well, I mean, use the shift theorem or just put alpha equals to 0, whatever floats your boat. But it's also worthwhile to notice that the cosine beta t has Laplace transform s over s squared plus beta squared. And the Laplace transform of sine beta t is what? It is beta over s squared plus beta squared. So for pure sines and pure cosines, we just get an unshifted quadratic in the denominator, which if you think about the role that the characteristic polynomial, the characteristic equation has played in this course, it's kind of not surprising. That's the algebra we keep seeing. Let's see here. So we got constants, we got exponentials, we got sines, we got cosines, we got exponentials times sines and cosines. What more could you want? What's that? What's it? You'd say what? Why am I asking this question? Maybe I don't want the answer that I'm going to get. Was some sort of snarky thing just told to me I couldn't quite hear? No? Excuse me. Another thing we could, here's just kind of a weird thought. If y is equal to the integral from 0 to infinity, right, y of s, is equal to the integral from 0 to infinity of e to the minus st little y of t dt, right? What happens if we differentiate that equation, which is the definition of the Laplace transform? What happens if we differentiate that with respect to s? What's dy ds equal to? So that's, you know, we can move the DDS inside the integration by analysis that we never cover in any courses here. DDS of e to the minus st. I mean, maybe it's covered in real analysis. You guys taking real analysis? Yeah, some of you. Actually, there's a good chance that we won't actually cover this in real analysis either. Real analysis tends to get tied up in like minutia of the real numbers and stuff that I don't care about. Oh, sorry. Nothing wrong with that. It's traditional, right? But anyway, you need to study uniform convergence and some other things to prove that you can do these. I mean, to do that, we're exchanging two limits. Anytime you exchange two limits, it begs a somewhat subtle and difficult question. But it can be done, and it's in fact valid to do this. And when you do that, what happens when you differentiate this? And I'm really taking a partial derivative with respect to s, truth be told, right? I mean, I'm holding t fixed in this differentiation. So what happens with the t? Yeah, we get e to the minus st again, right? And what's dds of minus st? It's minus t, right? So we get minus t y dt. Again, if you step away from the board, tilt your head, squint properly, you should identify that this is the Laplace transform of minus t times y. And if you keep doing this, like what would happen with d squared y? ds squared, what would that be? What happens when I apply this thing I just derived a second time? We get minus 1 times minus 1, the Laplace transform of t squared times y. So if you look at this, what's the pattern? If we let's see here, if we calculate the nth derivative, right, of the Laplace transform of y with respect to s, that will give us minus 1 to the n, the Laplace transform of t to the n times y. So this is actually a theorem. Why is this theorem helpful to us in our current endeavors? We're trying to figure out Laplace transforms of different functions, right? So what does that one give us access to? What if you set the function y to be 1? So like apply this to let y equals to 1, right? If y equals 1, then we'd have minus 1 to the n, right? The Laplace transform of t to the n. What would it be equal to? It would be equal to the n-fold derivative with respect to s of what? What's the Laplace transform of 1? 1 over s, right? What happens when you differentiate 1 over s n times? We get minus 1 from the first derivative. Then the second derivative gives me a minus 2, right? The third derivative gives me a minus 3. All the way out until I get to the what? The nth derivative gives me a... let me think about this. I got to keep myself honest here. What happens with like n equals to 2? Let's just look at that to make sure we don't get the wrong pattern. Aha. So it actually gets to the... So the numerator, in fact, goes to minus n, right? But the denominator is s to the n plus 1, right? But you notice that you could write this as minus 1 to the n times n factorial over s to the n plus 1. So what did we just derive? We've got this is equal to that. Therefore, the Laplace transform of t to the n at s is equal to n factorial divided by s to the n plus 1. Hooray! Now we've got constants, exponentials, sines, cosines, exponentials times sines and cosine, and monomials. You're fine. Your t squared, your t cubed, your t to the fourth. Now, think about this for a second. What if I hadn't differentiated the integral to derive this? What if I just gone straight from the definition? What would we have had to have done? Words. Like, think about that. You'd end up integrating e to the minus st times t to the n. I mean, we can do it, but this is much easier. Anyway, at the end of the day, we need the boxed equation to work with, all right? But I think it's important for you guys to see where these things come from. Also because the calculations we're doing are not disconnected from the ones that you'll actually need to do to solve problems in here. If nothing else, they're a good exercise in algebra. Now, on the next test, you are allowed a sheet of notes. And I would recommend that you use this as your sheet. You may write in between the lines, and you may fill the back with whatever you'd like. I mean, Elizabethan poetry, Psalms, Proverbs, whatever, Ecclesiastes, the words to Gnarls Barkley's Crazy. I mean, whatever.
Are we allowed to use all 6 sides of the
You may only use 2 sides of the paper. The other 4 sides must remain unmarked. I like that you chose this paper to have 6 sides. I mean, why not add four extra time-space sides to the paper? Did I? No, okay. It's yeah. So, oh, I mean, that was a suggestion. You may, again, the paper that you can bring to the next test is this size, is my point. It doesn't have to literally be the paper I just gave you, but if I was lazy, I would do that. I mean, let's take account here. What have we learned? Table 7.1. We have derived 1, e to the t, t to the n, sine, cosine. The only thing missing here is the 1, 2, 3, 4, 5, 6 thing down. But how would you derive that? How would you? That will be totally out of focus, but it's fine. How would you derive the 6th thing down? Yeah, the shift. You should apply the shift theorem to this. You get the 6th one, right? So the translation and t thing, I will probably do a different day. The transform of a periodic function, I don't tend to cover in here because I don't know any good homework problems for it, and it's really, really fun, but I don't cover it. Convolution we will cover, but that will be not today. So really the only order of business here left is to try to derive the other theorems in table 7.2. You notice we've already derived the last one in table 7.2. That's this. The last thing in table 7.2 is exactly this. But it's written in the L notation rather than the big Y notation. Do you see that they're the same statement? See that? The Laplace transform of t to the n times, so think of the little y as being the f in the table. Y equals the little f. Well, that's the nth derivative of, let's see here. You know what? It's probably just a good exercise for me to translate that boxed equation into the other notation, since we're still learning, right? So I'm just kidding. Sometimes I say that I'm still learning things. It's not true here. It's just not. The point at which I will learn things about Laplace transforms in this course is past, I'm afraid. So here's what that statement looks like written in terms of the L notation, which is exactly the last thing in table 7.2, right? Okay, so one piece of the puzzle remains, which is how do we take the Laplace transform of a derivative of a function of time? Those are the results at the top of table 7.2. By the way, you should also appreciate that my example 3 dodged the bullet as well, because if we had faced it directly from the definition, we would have found ourselves integrating exponentials times sines or cosines. Yeah, but we didn't do that, did we? Yeah.
What is, so on the sheet of paper, the last Laplace
You got it.
It's gamma and then n plus 1. Isn't that what we derived
Gamma is the gamma function. So what if t is not a whole number? What happens if you take the Laplace transform of the square root of t? There you'd need to introduce the gamma function. The gamma function is essentially a continuous extension of the factorial function. So it agrees with the factorial in a specific way at integer whole numbers. It's not directly it. It's like shifted. So that is something I should probably talk about next class, most likely. I sometimes forget. I almost never have test questions which are on anything except for like taking a Laplace transform of t or t squared or t cubed. But it is true we should know about the gamma function for non-integer powers of t. Yeah, and of course the gamma function has deep and interesting meaning as it connects to other things in number theory and just classical analysis. But although those things I'm tempted to talk about, I probably shouldn't talk about. Well, I don't know. I will make a point to try to talk about the gamma function next time since you asked. But I didn't bring my book, and I don't remember its definition right off the top of my head, unfortunately. It'd be my luck to be off by like 1 or something, and then I'd regret. So, okay, so next question is, let's calculate the Laplace transform. And I'll use a y rather than an f here because it's just prettier. So you want to calculate the Laplace transform of dy dt of s. And we're assuming that y is of exponential order alpha so that you can actually make sense of that. All right. How do you do this? Well, by definition, this is the integral from 0 to infinity, e to the minus st dy dt dt, right? So we'd like to relate this to the Laplace transform of y, if possible, right? So the thing to think about here is integration by parts, but I will do it directly. Rather than doing integration by parts, I will just point out if we take the time derivative of e to the minus st times y, what do we get? We get minus s, right, e to the minus sty plus e to the minus st dy dt by the product rule. This time I'm differentiating with respect to time. That's why a minus s pulled out, in contrast to my last derivation where we were differentiating with respect to s and a minus t pulled out. But this guy right here is what we already have. Right? So I can trade that for the derivative of the product plus s times e to the minus sty. Does that make sense to you guys, what I did? I hope it does. All I did was to take these two pieces and put them on the same side and replace the green with the red. Product rule. But now we're looking at what? The integral of a total derivative. So again, implicit limit notation. Right? We can pull the s out. Why? Because s has no, well, s is not a function of t, right? So I can pull it out of the integral. Now, to be clear, that evaluation is happening where, and I mean, to be more pedantic, this is y of t, right? And this is at infinity equals to t and t equal to 0. I mean, those are the bounds there. So what happens when we plug in infinity? You're like, we don't plug in infinity. We take a limit as a variable approaches infinity. I don't know what you're talking about, sir. Very good. We taught you well. But the point of the point here is that y of t is got exponential order alpha, which means that it's smaller than some exponential, which really means that e to the minus st wins. In other words, that when we plug in infinity, that the infinity term has to go to 0 because of exponential order alpha. On the other hand, the 0 term gives you what? E to the 0, 1, and so minus y of 0. And what's this? You should recognize this is the Laplace transform of y. Written in a slightly less cluttered notation, we've just shown that the Laplace transform of y prime, right, is equal to s times the Laplace transform of y minus the initial value of y. You're like, that's great, but I would really like this if you could write it in yet another notation, please, because it really makes me happy when you use like 3 different notations for the same thing, because that helps me understand more. And I was like, well, yeah, okay, I can do that. But in my defense, these are all standard notations. And they each have their calculational role. But anyway, here, the Laplace transform of dy dt, here's how I actually tend to use it, of s, is s times big Y minus y of 0. This is what I used at the example at the start of class. Well, not quite, actually. That's not honest. Sorry, we're not there yet. What happens when we... Well, let me stop. Any questions about this? It's kind of important. Because our goal is to solve differential equations, right? What do differential equations have in them? Derivatives, right? So taking the Laplace transform of derivatives, that's so much of what we need to do. This is the bedrock of that, right? There it is. What if we take the Laplace transform of y prime prime? That's equal to what? That's actually the Laplace transform of what? Y prime prime, right? So if we apply what we just did to the derivative function, we immediately get s times the Laplace transform of y prime minus y prime of 0. But of course, we can take that and trade out our Laplace transform of y prime for s times the Laplace transform of y minus y of 0. Of course, I've still got my minus y prime of 0. And so let me clean it up one more step. We've got s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. And there you have it. That's the Laplace transform of y prime prime. Let me show you the notation I usually use as it arises in problems. The Laplace transform of y prime prime at s is equal to s squared times big Y minus s times y of 0 minus y prime of 0. Same theorem, same result, different notation. What if we had 3 derivatives? Prime, prime, prime. We got s cubed y minus s squared y of 0 minus s y prime of 0 minus y prime prime of 0. Etc., etc. The et cetera is on your table, right? If you look at the table, 7.2, you notice the next to the last one there, the nth derivative of f, s to the n, Laplace transform of f, minus s to the n minus 1 f of 0, minus f to the n minus 1 derivative of 0. So to calculate the Laplace transform, we either need to be willing to incorporate symbolic initial conditions or to actually have specific numerical initial conditions to sort of fold into the solution as we take the Laplace transform, but that's it. All right, I have a few more tools to share with you concerning discontinuous functions, and we should talk about the Dirac delta function, which isn't a function. Perhaps we should talk about the gamma function, right? But I'll save those things for next time, most likely. If you go back now, you can understand what I did at the start of class, right? We had what? We had y prime prime plus y. Let me say y prime prime plus y equals to 0, just to give you an example, which is like the one at the start of class, but not quite as complicated. This is example what? What is it? At least 4? 5 seems safe. Example 5. So let's suppose we got, this is 4? This is 4? Oh. All right. You guys give me initial conditions, whatever you want. What do you want? What's y prime of 0? What's y of 0? 1 and I'll take your 5 and make it a 6 because my 5s and s's look too much alike. So there you go. That's an initial value problem. How would we solve it with Laplace transforms? Here's how you do it. You take the Laplace transform. We get s squared big Y. Now, what do we do? Right here, minus s times y of 0. What was y of 0? You guys told me it was 1. And then minus y prime of 0, which you told me was 5, but I made it 6. So there we go. And then plus big Y equals to 0. There you go. We took our differential equation. We made it into an algebraic equation. This is the magic of the Laplace transform. Next step in the game is to isolate the big Y. So that gives me s squared plus 1 times big Y equal to, looks like a 6 plus s. All right. So I solve for big Y, which I'm going to do up here because I'm tired of writing down there. Poor planning on my part, sorry. Y then is equal to 6 plus s over s squared plus 1. Now, what are we after? We're not after big Y, right? We're after little y. Little y is the solution to the differential equation. How do we find that? Let me write this a little bit more, just kind of in your face here. 6 times 1 over s squared plus 1 plus s over s squared plus 1. So little y is the inverse Laplace transform of big Y. And that will be equal to 6 times the inverse Laplace transform of 1 over s squared plus 1 plus 1 times the inverse Laplace transform of s over s squared plus 1. Because guess what? The inverse of